When we do our practice problems, it's important that we follow all the same steps that we do when we solve any type of physics problems. That is, we're going to draw a picture with the coordinate system indicated. We're going to draw, in this case, graphs of the motion of the object, position, velocity, acceleration graphs. We're going to have a table of all the known values for the kinematic quantities. That's position, initial and final, velocity, initial and final, the acceleration, and the duration. We're going to look for a target variable that we're trying to solve for in the problem. We're going to figure out which equation, or maybe equations, we need in order to solve for it. We're going to look for an algebraic solution for those equations. And then finally, we're going to substitute everything in and get our answer that we're looking for. So for our first problem, we're going to look at this scenario here. We have a cannonball that's on the top of a 12.5 meter tall fort, and you're dropping the cannonball, and we want to know how fast is it going when it hits the ground. So the first thing we want to do is draw a picture of the scenario. I am going to attempt to draw the scenario in Google Drawings. Let's see how it's done. So here is fort. I don't want to blue though, let's make it gray. There we go. Okay. And we need ground, so we'll draw a line for the ground. And move the fort onto the ground. Okay. We need a cannonball. There we go, there's a cannonball we're going to drop. And it's not very important that you are in this picture, no offense. But let's see if we can get a little, it's going to be pretty hard with the locks on. But here is a little picture of you. I think we can group these together. There we go. Okay, there we go. That works. Completely unnecessary. So here's our picture of the scenario, but we need to add a coordinate system to this. And the two most important things about a coordinate system are going to be what direction is the coordinate that we're going to be measuring in, what direction is the positive and negative in particular, and where are we counting 0? Where is the origin for our problem? So there are technically infinite number of answers to this, but I'd argue that there are two most sensible answers. And so the answer that I think we can use for this problem is for y to point upward. So we can label this x over here, and we can label this one y over here. So that means that as you move upward, you're getting more positive values of y. And we're putting the x-axis down here at the bottom, so y equals 0 at the bottom of the fort. Another reasonable answer would be to put the x-axis where the ball is starting. So now you're saying, oh, it's 0 meters here, but it's going to be going to negative meters as it falls down. That'd be fine. Technically, you could put it in the middle here, right? And so it's starting at positive something or other meters and end up negative something or other meters. I don't know why you would do that, but you could. There we go. There's our coordinate system with the picture. Okay, the next thing we need to do is to come up with the graphs. So let's think about what we expect to happen here. We can go ahead and open our graphs over here. This is going to make a copy of our coordinate axes. By now you should have an idea how we're going to actually create these graphs. I like to start with the acceleration graphs and go from there. So we have an object, it's starting at a large positive x, I guess y value, and we expect it to become closer to 0 as time goes on. And that's because gravity is pulling it downward. Well, what direction is downward in this coordinate system? Up is the positive direction, and so downward is going to be the negative direction. So we have a negative acceleration. We would try to make that look a little constant, like that. Okay, what does velocity look like? Well, the problem says that we drop the cannonball. Drop implies that the velocity is starting at 0. So our velocity is going to start at 0 mark. And as it's falling, it's going to be moving faster, but downward in the negative direction. So the left point needs to start there, and then as we progress, it needs to be moving more and more negative. And finally, position, starting off slowly, it's going downward and speeding up. And so from our 4 curved choices, we need one that is moving downward but getting steeper. These are the 2 that are moving downward, but this is the only one getting steeper. So those are our 3 graphs. So I'm going to pretty quickly download these and put them into our plan. Okay, so now we have a coordinate system, we have a graph. So now the next thing we need is to write out our known values. So in particular, when we're doing a kinematics problem, what I recommend is to make a table, and the table needs to have 6 columns and 2 rows. In the first row, you're going to put in all of our kinematic variables. So we have the x position, or I guess technically we have y, right? So y initial. We have y final. We have the velocity in the y direction initial. We have velocity in the y direction final. We have the acceleration in the y direction. And then finally, we have the change in time. The best way to get that is to add an equation, go to Greek, delta t. Okay, we're going to think about each of these values, whether we know them or whether we need to put a question mark because we don't know them. So let's look at our diagram and our problem. Okay, when the problem starts, we are 12.5 meters high. When the problem ends, we're on the ground, which is 0 meters high. So that sounds like we do know our initial and our final y values. For the velocity, it says that the ball is dropped, right? So that is telling us that our initial velocity is 0. But nothing is telling us what the final value for velocity is, right? We know that it's a negative value, but we don't know what the number is. Acceleration, we know it's negative, but we also know the specific value, right? Because this is free fall, and so we know that the value is 9.80 meters per second squared. And then finally, we do not immediately know how much time it takes, right? So that is the 4th tick mark, but nothing immediately tells us how long that's going to be. So if we look at these and we consider our equations, we want to pick one that has all the values that we know plus the one that we don't know that we're looking for. And the one that it is this one, right? We know how much distance we've covered. The delta x, of course, it's y, right? But those are, you can replace those two with one another. We know what the acceleration is. We know what the initial velocity is, and we're looking for the final velocity. So this is the equation that we're going to put in. So this is the equation that we're going to put in for our solution. So we have v Fy squared is equal to v Iy squared plus 2 times ay times Greek delta y. Okay? Now, we are not ready to put in numbers for that yet. We need to solve for our variable that we're trying to find, and that, of course, is the Fy. I don't worry too much about the order of these subscripts. We know that y is the direction we want to go, and f is the final or initial, in this case final, right? So we're going to solve for that. And the solution in this case is pretty easy. We're just taking the square root, but there's something we have to pay attention to. So it's v Fy is equal to what happens when we take the square root of both sides, right? We get a plus or minus. So we have plus or minus the square root of v Iy squared plus 2 times ay times delta y. Okay? Now, if we think about what we know from the solution we want, we can select whether we get the plus or minus solution. And we know that the velocity value that we want is going to be the negative. And so for our next value, we can have v Fy is equal to the negative square root. Viy is 0, so we just plus 2 times a y plus delta y. I do allow you to plug in zeros before the step where you plug in all the values. And finally, we're ready to plug in the values. So v Fy is equal to a negative square root 2 times, now it's important that we put in all the signs correctly. Remember that ay was negative 9.80 meters per second squared, because the delta y final was 0 and the initial was the 12.5 meters. So now we can just get out a trusty calculator and figure out what the number is, and the number is equals 15.7 meters per second. Now, this is the velocity, and now you have to pay a little bit of attention to the question actually asked. How fast is it going when it's the ground? So the speed is equal to the absolute value. So v equals absolute value of v Fy, no, 15.7 meters per second. 15.7 meters per second.